So what's a paging? Paging is kind of advances from segmentation. Segmentation is nice in the sense that it provides a memory to a process in an amount that actually process is needed, right? In that sense, segmentation have an advantage in utilizing memory resource of the computer system. But the drawback of the segmentation idea is that by allowing variable length memory unit, I mean, memory is given as a various length region, the management requires more sophisticated algorithm, and there's no real solution toward external fragmentation problem if we just allow variable length segments. So people have devised different mechanisms to overcome those limitations, and while taking the advantages and nice aspects of the idea of the segment, so people find a kind of nice solution that is called paging. Idea here is that allocate the amount of memory to a process as a set of small fixed pieces. Not give a huge chunk or not give a variable length chunk, but a number of slots. And here slot means fixed size unit, and the size is not that big, and it's a small size unit. So for example, if a process requires like 19 kilobytes, maybe instead of providing huge memory space for covering all address space, and not just to give exactly 19 kilobyte, but give, for example, 5 of 4 kilobyte slots. So each slot consists of the 4 kilobytes, and every slot has the same size of the memory. And by having fixed size unit, management of those fixed size units are much easier than managing variable length units. And we just give a 5 unit of them. Then we can satisfy the request of having 19 kilobyte memory. But the problem, one problem here is what? We have another internal fragmentation issue in this case. In this example, it received 20 kilobyte. So there is a 1 kilobyte left, which cannot be used by other process. So it'll be just wasted. So internal fragmentation problem can happen in paging idea, but the drawback is limited. Why? Internal fragmentation can happen, but it will not exceed 4 kilobytes, right? Because memory is given in a multiplier of 4 kilobytes. So remaining portion of a memory cannot exceed 4 kilobytes. And in average, it'll be like a 2 kilobyte. So this is not a big deal. I mean, sacrificing 2 kilobyte in average for each process is not much a deal, comparing to the benefit of having fixed size memory unit. Because once we use a fixed size one, then management becomes really, really easy. So they later have a better chance to provide, increase the utilization of the memory. So benefits are more than disadvantage. So paging is a nice idea. So it's widely used in almost all systems today. Almost all computer architecture system today actually use a paging. So how it is implemented. So system divide an address space. This is a one that belongs to the virtual world, right? Address space into a pages. And at the same time, the system divide a physical memory space. This is a word of hardware, right? Into a frame. So it's a page here, virtual memory unit is called pages, and physical memory unit is called as a frame. So they are two different concepts because they are belonging to the two different words, but make their size the same, and their size should be the same. Then what? One page can be mapped to a specific frame in the physical memory. So mapping become really simple. I mean, specific number specific page identifier can be just mapped to a specific frame identifier, then memory allocation and memory alignment shall become really clear and easy for operating system to manage. Okay, that's the idea. And this one nicely resolved the internal and external fragmentation issue. So here's a depiction. So thinking about this computer with the address space, and here the address space is 64 bytes. What kind of a computer it is anyway. And here we have a physical memory of 128 bytes. Yeah, huge space. And if we have a 16-byte page and 16-byte frame, I mean, those numbers should be the same, always the same. I mean, we will extend this notion later, but here so far, let's assume that the size of the page and frames are exactly the same. 16-byte page and frame, then you see that virtual memory space can be split into 4 slots. We call each one as a page. Make sense? And then physical memory area is divided by the same, divided in the same unit, 16 byte. So there should be 8 frame. So here the frame number 0 to 7, and here is a page number 0 to 3. And each page can be allocated to certain frames. So in this example, page 0 is mapped to here. Okay, mapped to here. And systems do not need to memorize the base and bound register. Why? It can be simply computed from frame identifier. Right, so it's easy. The things that's just to memorize is which frame number is a map to a specific page number. So it's easy. Maybe if this page is, so in this example, page 1 is a map to here, and page 2 is mapped to here, and page 3 is here. But if the process is not allowed to use some pages, that's possible, right? I mean, address spaces are usually larger than the amount of the memory given to a process. In such a cases, maybe system just disallow for a process to use page number 2, for instance. Then maybe there is no mapping of the page number to found in the physical memory. Okay, so this is how paging is working. Okay, so page table. So here we talked that pages are mapped to a frame, and these mappings should be represented as a data structure inside of a kernel, and that data structure is called page table. So page table exists for a process, which means that there are multiple processes. Basically, we need to have a multiple page table, because page table is a mapping between virtual page number to a physical frame number, right? And virtual page number belongs to a process, which means that if there can be a multiple pages that have the same number, page number, across multiple processes. So page numbers are something specific, something that belongs to a process. So to make a distinction of pages of different processes, we need to have a page table for each process. 여러분 집에서도 첫째, 둘째, 셋째가 있으면 형제들이 있으면 집집마다 첫째가 있잖아요. 집집마다 첫째가 있잖아. 그러니까 예, 그거는 집에서 쓰는 말이죠. 그러면은 집집마다 페이지 테이블이 있어야겠죠, 그렇죠? Okay, so by default, page table exists per process, so that is called as a per process page table. But there is an alternative structure called inverted page table. This is kind of an inverse. Its form is inverse of this original page table, such that the key part of this mapping is letter physical frame number. So this is a key, and the value part is a virtual page number. But virtual page number cannot be distinguished. It have a limited information to identify the exact page. So we need to give a process ID together with the virtual page number in inverted page table. And why we need this type of a strange structure? Because if we keep the page number for every process, then system will need to spend a lot of memory solely for storing page tables. It's a kind of an issue. It's kind of a big issue. And we know that even though some pages are given to a process, not all of them are actually in use. Or later, only a few of them are actually in use. So page table wastes a lot of memory space, especially for the system like a piece, which are for like which accommodate like 1,000 processes at the same time. Yeah. So to save up some memory for page table, some modern architecture system, they later keep the page table as a inverted page table. I think hopefully we can discuss this issue after discussing about swapping. So after midterm, I guess we will revisit this issue. At this moment, you just understand it this way and move on. Okay, so how translation happens? Address translation happens. So this way. So here, this is a virtual address, and virtual address here consists of 6 bits. Wow, 6 bits. And as with similar fashion as we do for the segmentation, we can assign few top bits as a virtual page identifier or virtual page number, and these bits are directly translated into a virtual page number. And remaining things should be used for offset. Offset is a relative address inside of a page, right? So what will be the capacity of the page in this case? Since offset consists of like 4 bits here, so capacity of a single page, which is the capacity of a single frame here, is what? 2 to the 4, which is 16 bytes. 그쵸? Fair enough. Okay, here. And architecture refer this page table to find corresponding PFN, physical frame number of this VPN value, which is a 111, then replace this part into a PFN, then this becomes a physical address of this address. So far clear? This is kind of nice, right? I mean, we don't really need to care about difficult things about a base and bound register, and everything is really simple once we have a page table. But what will be an issue here? The issue is that where this page table resides, it resides in main memory. Then what will be a problem? For making a memory access, we need to reference memory again. And if an instruction concerns multiple memory references, then what? I mean, the number of the page table access will also increase by that, which means that your computer becomes twice or more slower than ordinary case when you use page table. 무슨 말인지 이해돼요? 그러니까 메모리 레퍼런스를 하기 위해서 페이지 테이블을 봐야 되는데 페이지 테이블도 어디 있어요? 메모리 있어. 그럼 메모리 2번씩 봐야 되는 거예요. 뭐 까짓 거 2번씩 보면 됩니까? 그랬어도 되죠. 그래도 되죠. But this is a big issue for ordinary person. And the reason why this matters is that, I mean, what if we just put the page table inside of a computer architecture? Then everything will be really fast. But the issue is that typically page table is pretty large. So for example, so this is a more realistic setting. Suppose that we have a 32-bit address space, and 4 GB memory. So this is also 32-bit. So here we have a 32-bit address space and also 32-bit physical memory space, right? And we have a 4 GB page and frame. 4 kilobyte page and frame. And how many bits are needed as an offset for this page and frame? offset은 몇 비트 필요하겠습니까? 2 to the, so 4 kilobyte is 2 to the 12, right? So 12 bits are needed for representing an offset part of a memory address, right? And how many virtual page number can exist? For the amount of thing that can be represented by 20 bits, isn't it? Which means that when we create a page table, how many entry must exist? Two to the 20 entry must exist in a page table. It's not small, right? And if one entry of a page table requires 4 bytes, then it takes 4 megabytes for a single page table. Sorry, my phone is keep ringing. But the issue is that, yeah, typically computer system runs like at least 50 processes for different daemons. And like a piece case, it runs like thousands or multiple thousands of the processes. Then how many? So if we just use 100 processes, actually your laptop at this moment running more than 100 processes, I believe. If this happened, then 400 megabytes should be used solely for holding page tables, which is a pretty large amount of memory. And obviously, these cannot be stored in computer architecture level. That's kind of an issue, right? Yeah. Then what? Yeah, it should be placed in somewhere in memory. Then which means that for every memory access, we need to pay extra memory access for referring page table. It's a kind of a huge penalty. Good job. So even though how novel the page table idea is, if reality is like that, this cannot be a feasible option. So people have found some solution toward this issue. So we will discuss about that. But before going into that discussion, let me give a little more information about the page table, especially what kind of attributes are there in page table attribute entries. Page table entry in a single row in a page table. I mean, in a single row of the page table, we essentially need to have a PFN, physical frame number. So suppose that page, so you can think in this way, page table looks like an array. So given VPN, you can use the VPN number as a kind of an index of this page table array and retrieve the element of this array. And this element at the VPN index should contain information for some page translation, page to frame translation. Okay? And essential information an entry should have is PFN. 그렇겠죠, 그죠? However, one thing you notice that PFN cannot be as large as full address space digits. 그렇죠? So for example, in this example of x86 32-bit, it uses ordinary cases for 32-bit virtual address. This is a virtual address. 12 bits are used for representing offset parts. So PFN can be only like remaining 20 bits. And 12 bits may not be used in a part of the page table entry. But in actual, these remaining 12 bits are used for representing different property of a page that it concerns. What kind of properties are there? First property is about valid bit. Valid bit. This can be a single bit, valid bit. What it means by valid? You know that not all pages will be actually given to a process. So some pages are given and in use and valid, whereas some other pages are not given to a process. OS does not give that to the process. Then such pages should not be accessed. And those ungiven pages are marked as invalid. So page table need to have this attribute. Make sense? Okay. And what else? And present bit. Present bit represent for a valid page that whether the page content is actually reside in physical memory or it reside in a storage system. What does it mean by having it in a storage system? You need to study. We need to study swapping for understanding this one. Yeah. So just wait, and we will talk this issue over after midterm. Okay. Just skip it. Okay. Just what you need to have in mind is that, yeah, to complete the virtual memory system, we will extend the physical memory by augmenting some portion of the storage system. And there are some issue and interesting things are there, and this is prepared for that purpose. That's amount of understanding that you need at this moment. Okay. And permission bit. Permission bit represent whether the page is a read only or read and write. And some page can be set to be super mode only. Set to be super mode only. So under the super mode, certain page can be retrieved, but certain pages cannot be used under user mode. That kind of attribute. There can be many attributes. Actually, x86, many of these bits are of permission bits. So those kind of bits are taking some portion in page table entry. And another thing is dirty bit. This is also relevant to a swapping issue. So thinking in this way, some page contents was originally placed in a storage, and then it will be loaded to the memory. And then what if the page never be written? So the contents does not change at all after the loading. Then we have a confidence that the contents are exactly the same as the one in the memory and one in the storage, right? To count that information, yeah, architecture count the dirty bit. If dirty bit is on, it means that, yeah, there's some writing on the pages. And if dirty bit is off, it means that this page has never been changed so far. So how will it be used? Please wait. Yeah, we will talk this over after midterm, right? And reference bit is also relevant to the swapping issue. And this one indicate whether the page has been recently accessed or not. So to identify whether this page is hot or not. Hot means it's a frequently used pages. And if it is a core, then it means this page is rarely used. And it might be somewhat useless in some sense. Yeah. And this is also relevant to the swapping issue. So we will talk that later. Okay. And this is a more detailed step that happened under the computer architecture for translation. So check this logic. Before that, I'll let you know to note that please remark that this is a pseudocode algorithm, and these algorithm is actually implemented in the form of the hardware, so that this may not be executed sequentially, but it can be run in parallel, or ordering of the execution of some instructions are not really enforced. 이거 소프트웨어로 도는 거 아니에요. All these are encoded as a hardware under the computer architecture. Have that in mind. But this is to represent the logic of the computation. This pseudocode is just for representation of the what kind of thing happened inside of the computer architecture. So for translation, what you need to do is first obtaining this VPN value. By how? By putting some mask and do the AND operation. Then you can filter out all the offset part you can just gather the VPN part. So for example, mask here will be like 110000. 그쵸? Then you can just obtain this part and then do some right shift. Then what? You can get VPN number. And using this VPN number, what you need to do is that you need to find the corresponding entry. I told you that page table is stored in a form of an array in memory. So there's some starting point of the page table, which is represented in PTBR value in this pseudocode. And having VPN as a kind of an array index, we can find the exact location of the PTE page table entry by multiplying VPN by size of the page table entry and add it to the starting point of an array. 그렇겠죠? Then you can get the exact address where page table entry exists. And then you access the memory to retrieve the page table entry, right? And then what you need to first check is whether the page is valid or not. Valid meaning it is something given from the operating system to the process. But what if it's invalid? What if this is a false? Then what? Segmentation fault. This is unallowed to the process. So it just raise an exception. Make sense? It's a kind of a protection mechanism, right? Yeah. 이해하기 힘들다는 표정으로 많이 쳐다보고 계시네요. 그럴 수 있지. 좀 있으면 모르겠으면 질문하세요. And what if, and even if the page is valid, what if the protection bit says the process is not allowed to access this one? Then it also throw an exception, protection fault, and everything is all right. Then it actually perform memory access. But for doing that, we need to translate the VPN into a PFN. So in order to do so, yeah, we first get the offset part. 요것만 offset. How can we gather the offset? By using a mask like 이거 어떻게 돼야 되겠어요? 001111. And if it is logically ended with this value, then we can only get an offset part, right? And then what? We retrieve the PFN and place it in the proper digit by shift operation, and then make a addition, logical addition with the offset part. Then the resulting number will be physical memory address, so make a memory access here. So this code also shows that for each memory access, we got to need to have another memory access prior to the real one for page table translation. Have any question?
교수님 혹시 그 쉬프트 하는 부분 조금 한 번만 더 설명 가능하실까요?
네, 좋습니다. 자, 아니 근데 이거는 쉬운 거 자꾸만 가르치면 안 되는데 쉬운 거 자꾸만 가르치면 어떻게 될까요? Think about having logical AND with this one. Then what? 0 0 0 0 1 0. Make sense? 그렇죠? And then I'm doing this one. I'm doing this one. And shift for how many times? 4 times. Shift once. Shift twice. One more time. One more time. This number. Okay. Okay. So before moving on more discussion about paging, so here's an example how actually memory access happens once we execute this piece of code. So this piece of code will be translated into this form of an assembly language. So what will be this one? It starts from $, so it means it's a constant, and this is in hexadecimal representation. So this is what? It means 0. So it's a move. So assign 0 to where? This address. What do you see here? It seems like what? A relative address, isn't it? And so once you carefully see, it's a relative address. So it's for accessing this array, the ith element of an array. And this one is actually representing I. And this is a 4 byte. Possibly this is a kind of an integer, I guess. So every 4 byte, the digit jumps. So not digit jump, but index jumps. Index jump in the unit of the 4 bytes. This is a kind of a base register for representing the starting point of an array, right? So this means what? Array I, isn't it? So assign 0 to array I, and then what? Increment I. Okay. And then compare what? This is also constant, right? What exactly this value is? Don't know. Who knows? Who knows? But you will soon find that this one is what? Actually 1000, I guess. 1000. And compare 1000 with the EAX. Compare 1000 and EAX. Typically, which one will be larger? 1000 will be larger, right? In such a case, jump to the, this is the address, 2124. Yeah, jump to here. But if the comparison returns that, yeah, the EAX is a large, then what? It is just to move on to the next instruction after jump. 이렇게 되겠죠? So thinking about that, the computer system actually execute this piece of the code for many iterations. And this is the depiction of memory access. Here, this is a timeline. And this is a physical memory space address. And each dot represents memory access at the moment. Thinking in this, so it starts from what? Accessing the location 124, which is the location of this instruction. Why? In order to execute the instruction, we need to fetch the instruction. We need to actually fetch this instruction. So in order for making fetching, we need to have a memory access. Good job. And that is this one. But to make a reference on virtual address, what we also need to do is what? We need to access, page table for that. To interpret 124 into physical memory address. So in executing this statement, we need to have a double memory reference. Isn't it? 그렇죠? And then what? Yeah, after fetching as a result of its execution, it assigns 0 to this address where it is. It resides in here. I don't know, but array start from 40,000. So it try to access this one, but we need to translate this address into a corresponding physical address as well. For that, we need to access another page table entry. For example, is reside in page table 39. Okay. For executing this instruction, it make a memory access once 4 times. Okay. And then what? And then program control go to the next instruction. So inc. So to fetch this instruction, we need to make a memory access. And for address translation, page table will be referenced. But it does not incur more memory accesses for execution because this is just for manipulating register value. Fair enough? And so on. This one also concerned about register and constant. So it also incurs memory reference here and page table access here. But jump, same here, here. And as a result of the jump, control go back to the 124 and it start from 124 again and repeat for a while. So once we capture the memory access pattern, it will shape like this one. What do you see here? What do you see here? Here, the message is that the address space is pretty large, and there are many page table entry, but within a small time window, only few page tables are likely get accessed. Why? Because few instructions are repeatedly executed. And also, if we concern about an array or variable, they are very likely that placed in a similar region in memory. And if we access code, this is also similar. The instructions are executed pretty much continuously. So consecutive instructions are likely to be executed as well, which means that same pages are likely accessed very frequently within a small time window. Yeah. That's kind of a characteristic ordinary computer program has. Then what? Okay, we know that page table is actually a large data structure, but in a short time period, only very limited portion of them are likely get accessed. Then why don't we have a cache inside of a computer architecture that hold frequently used portion of the page table so that page translation can quickly happen without really referencing main memory. That caching idea is actually widely used, and this is the idea that make paging practical. And we call that special purpose cache as a translation look-ahead buffer, TLB in short. TLB라고 부릅니다. TLB is a part of the MMU, so it's a hardware. It's implemented in a hardware level and working as a cache for page table. So this is a revised algorithm for virtual address translation. Things are pretty much the same as I explained it before, but here the change is that before actually checking the page table, what it first does is searching on TLB, which reside in a computer architecture, and to see whether there is any entry for VPN. And if there is an entry, let's holla and get the PFN from this cached information. And the translation does not need extra memory access, so it can quickly happen. We call this fortunate cases of LLB hit. It's a kind of a cache hit. But what if LLB does not hold the information for the VPN that is concerned? Then what? There is no need for that. Then there is no need, but we need to check the page table in memory. Okay, so go to the page table and get the PPN. Then here, computer architecture see that, okay, a new VPN information is now achieved. So it is very likely that this address or this page will be referenced again in the near future. So it try to store this VPN and PFN information at TLB because the same request can come in the near future in a high probability. And repeat from the top. So this is a kind of a changes once we have a TLB in computer architecture. It's kind of putting the cache layer in between the architecture and page table. Okay. So this is a kind of depiction of a TLB in use in computer architecture. So let me draw a boundary of the computer architecture here. So boundary of the computer architectures are here. Yes. Yeah, this is the word of the computer architecture. So for given virtual address is split it into an offset part. This is offset part and VPN part. And looking up the PFN of the VPN first at TLB. And if TLB hit occurs, then it's good. Just get that this is a page number, this is a frame number, so this is a VPN number, and this is a PFN. And if there's a lucky case, then just use this PFN directly and add it to the offset and get the virtual physical address and go to the memory to retrieve the data. But what if there is no proper entry for this VPN? Then what? We need to visit page table, which reside in a memory, main memory, and then get the result and use this PFN information. And one thing missing here is that this is also given to the TLB because it should be stored for future use as well. So this is how TLB work. It cooperate with the ordinary computer architecture model. So let me quickly cover this example. So suppose that we are executing this code. This is from your textbook, so you can easily see. So here the idea is that we assume that A0. So you will see that A0 is first to execute access, and subsequently A1 and A2 will be executed in a row, right? So what if we assume that A0 reside at memory location 100, and this is here. So initially TLB mishappen. Why? Because TLB does not know which PFN this VPN 6 is mapped to. But by executing this one, it updates the TLB, so it now know that the map PFN for page 6. And after that, if A1 is accessed, it belongs to the same page, so we can use a TLB information instead of retrieving that from the page table. What about A2? So TLB hits, so TLB works. It saves a lot of cost. But eventually it tries to go over the boundary of the pages. So now page changes, then maybe TLB happen again, and it also update TLB as well. So that maybe in accessing A4 and 5 and 6, same PFN information can be used. So this is how TLB can save up some memory access time. Okay, I think, and this is, I took it from my old textbook that this is a kind of a depiction of actual memory reference pattern. So this is execution time, and this is address space. And what do you see here? I mean, here the point is that access pattern of the memory is very sparse. So within a short time period, only limited portion of the memory are actually in frequent use, and the remaining are rarely used or never used at all. So at a time, only limited amount of memory is actually used.